Get started. Welcome to CS 196. This is week 9. Today we'll have a guest lecture by Microsoft, and then Duke will give us a lecture on machine learning. So some announcements to get started, I guess. No homework this week, so relax, have fun. We will have homework 5 out next week though, but for this week, take a break. So as an extension, office hours, we will have office hours on Wednesday. If you have questions about Python or anything in general, you can, we'll have course staff there in the same room, 11:05. And then we should have your, so 7 to 8 p.m. On Wednesday, which is tomorrow. And then we will have your midterm grades up at the end of this week. If any of you missed your midterms or haven't done it or don't know what a midterm is, please let us know, because that's a problem. We'll see if we can get stuff done for that. But if you had a valid excuse, though, we are technically required to give you a makeup. So let us know. Our emails will be put up soon. And then the hackathon is this Thursday, from 6 p.m. to 9 p.m. in 2405. We'll have some cool VR demos for you guys. And then also insomnia cookies at 8, it's a good chance, I guess, for you to cover up and make some progress on your projects if you haven't done too much, because midpoint presentations are going to happen next week in class next Tuesday. So some details are up there, but we'll just go through it real quick. You'll have about 3 to 4 minutes. No slides, but you can demo something if you want to. And kind of the goal of it is to just go over as a team kind of all the work you guys have done so far, and some roadblocks that you might have, or things that you have planned for the future. So it shouldn't take too long. We expect to get done with all of your groups in about 30 minutes. So that will happen next week though. So take time on Thursday, and if you need to have your normal meeting too, to make some progress on that. And then, of course, you can email us if you have questions. But before we get started with the talk, let's do a quick attendance quiz. There are only, I believe, 2 questions this week, and I can do it if you guys do. Select this, this week. Yeah, let me know when you guys are done, and then we can move on. I bombed it. I'm sorry. Guys done? No. No? Mostly done? Ish. Okay, we're gonna move on anyway, but it closes at 8:30, so you have time to do it. Alright, so we'll get started with our first lecture, which is by Microsoft. They'll be talking a little bit about Azure, but yeah, I'll let them introduce themselves and talk about it. Yeah. Yeah, we do.
Can you guys hear me? Oh yeah, we're good. All right, so hey guys, what's up? My name is Rohit Thodakora. This is Justin Bird, and we are the Microsoft Student Partners here on campus. If you guys don't know what Microsoft Student Partners are, we're basically almost like the equivalent for like a campus ambassador or a campus rep for the University of Illinois. And there's a bunch of Microsoft Student Partners for different schools around the United States. And we pretty much all do the same thing. We come endorse Microsoft on campus. We give a lot of workshops and talks like these about different services. Like today we're going to be talking about Microsoft Cognitive Toolkit, which is on their cloud Azure. So yeah, so I don't want to really spend too much time on the introduction. So yeah, so I'm just going to go straight into a little description about what the toolkit is, and then we're going to do a small little lab on how you guys can even use it to do some complex like neural networks / machine learning problems. So yeah, so the Microsoft Cognitive Toolkit is it was actually previously known as CNTK. Lets you, just a normal human being, utilize its open source to download and analyze giant data sets, mostly specifically for like image recognition, text pattern recognition, etc. And you guys probably know Python, obviously, and Python's the most widely used language with it, and you guys can really do a lot with it. So we're gonna keep going into it and explain it to you guys a little more.
So for this lab specifically, we're going to be kind of focusing on image recognition. So it's really difficult to obviously detect things in images. So this is kind of why this is what machine learning is good for. This is what it kind of excels at. And so just for an example, kind of what certain machine learning algorithms do is they try and find certain patterns in images. As you can see for the cat example, the ears, the eyes, and the mouth, they're all very distinct parts of the cat that can be recognized and kind of define what the cat is, at least in terms of the machine learning algorithm. And so for our demo, we're not going to look at cats, but actually handwriting. So if you're in 126, you'll kind of have an idea about that, because we had an MP on that, but we'll go into that later.
All right, like I said earlier, the Cognitive Toolkit really bases itself around neural networks. So what is a neural network? Does anyone here actually know how a neural network works? Or maybe like a high-level overview of it, anything? Yeah, so a neural network is basically a stem of machine learning where it almost acts like a human brain. Like that's why they call it a neural network, because it reinforces itself through learning, right? So the major overview here, like the overall thing about it is that, as you can see on the screen, on the right side there's a diagram. It has input nodes, which you see on the left side, and then output nodes, which you see on the right side. And in the middle you can see something called a hidden layer. And now neural networks have, they can have from one to up to as many hidden layers as you want. And what you call deep neural networks have a lot of hidden layers. And how these layers work is that you take, let's say, a picture of like the cats we saw, right, in the last slide. You can break that down into a couple of features and put those features into the input layer. And now, once you put those features into the input layer, your neural network, using those edges which are calculated probability edges, mathematically will connect those edges, almost like, let's say, think of your brain making connections as it jumps from synapse to synapse, right? Your neurons. In a similar way, it'll make connections through the hidden layers, and eventually your output will be decided by the neural network through those connections. So that is a little, it's a vague overview because there is really a lot, like mathematically, to neural networks. So obviously I'm not going to get into that, but that is what the Cognitive Toolkit runs on. So I just wanted to give you guys a little background on that.
Okay, so now talking about the toolkit specifically, free and open source, so anyone can use it, anyone can look at the code, see how it works. Like we said, it's in Python, which is what a lot of data science and machine learning, that's kind of driven by Python, but you can also use C++ and a few other languages there. And the files we're going to be working with are CNTK, which cognitive stand for the Cognitive Network. Cognitive Toolkit, sorry. And so those are going to be like the models that we're going to be looking at. They're going to be in the CNTK, which are specifically for this toolkit.
And yeah, the last slide before we get into the demo. So basically, to learn the toolkit, Microsoft has a lot of, even on its website, a lot of guides and examples and tutorials on how to use it. We're going to be using one of those from Microsoft's, one of Microsoft's open source GitHubs today. And you guys can learn a lot of things from, like I said earlier, image recognition to text recognition, etc. So we can give you the link at the end if you guys really want to get into it and try it out. But yeah, so let's move over to the hands-on lab.
Oh yeah, here's the link.
Oh yeah. So also at the end of the lab, we have like we're raffling off 2 Amazon gift cards. It's kind of weird because we're Microsoft and we're shopping Amazon things, but yeah, we have 2 gift cards for you guys. So we just need you guys to do a survey at the end, and yeah. So let's just get into the lab.
Does everyone have the link? Can I move on? So this is the lab page. This is what we're going to be following. It kind of gives an overview, which is basically what we talked about in the slides. And just another picture, basically, of the other one that Rohit talked about. And so for installing and installing the toolkit, it takes a little bit, so we're not going to go over that right now. We've already done it on this computer. But it's pretty simple. You just download it, and it gives you all the instructions. It's nothing too hard, but it just takes a little bit, so we're not going to be able to do it live. But nothing that you shouldn't be able to handle. So like I said, we're going to be using, we're going to be looking at some samples of handwriting and machine learning based off specifically the MNIST database, which is what we used in 126. So some of you might be familiar with that. And to get this, so once here, I'm going to open up a new command prompt. It's restart. So basically, once you've installed, can't hold this and type at the same time. So. Sure, if you want to. Yeah, so basically, you want to go to where you installed the CNTK files, or folder. Oh, yeah, we can use that one. Hands-free.
Does this work? Should we try this one?
Put it on your move it.
Blue? Okay. Thanks. Is it catching up? Okay. So basically, I'll just talk really loud. So to get into the CNTK kind of runtime place, basically you have to, this is all in the lab, but you have to, so basically this just puts you in a Python environment so you can run Python scripts and everything and the CNTK files. And this is explained again in the lab, so if you forget or something, you can look back at the lab and it will talk all about this. And so this just allows me to run Python and see into data files. So the first thing we need to do is we want to actually get the image data that of the handwriting so that we can train our model on it. So I'm going to go back. Into this folder, and so it has a Python file that's going to go and download the data, and it's going to put it into a format that our model can actually read. So I'm just going to run this Python. And so it's going to this website, and it's going to download this data so that we can read it and train using the data. So then when we go to that folder, I'll show you what it kind of looks like. So it's in data sets. So this is what the data actually looks like. If you did the 126 assignment, it kind of looks familiar. We have our labels, so what number the image is, and then these features act as the actual image of the, or at least a representation of the image in terms of numbers, and that's what we're going to be using for our model. So I'm just going to go back, and so we're going to be using two different models. One of them is going to be a one-layer hidden network. So like it's similar to the picture that we saw where there's just one hidden layer. And then we're going to be also using a convolution, it's called a convolutional neural network. And it's a little bit more complicated, but basically it was designed specifically for image classification. So we're going to predict that it's going to do a little bit better than just our one hidden. So to actually train our model, we're going to type in C, or it's a little bit better. So config, we're going to set the file to our hidden layer. And basically what this is going to do is, so now it's starting to train. You can see, so the first time, it's going to run through a bunch of, they're called epochs. And basically these are like training, like evolutions almost. And you can see every time, here the errors, I'll wait till it's done. So you can see the first time that it ran, it had an error rate of 7%, which is, it's okay, but it's not the best. But every evolution, that error rate's going further and further down because it's able to train, and then it's testing it to see how it's doing. And then based on that test, it can, it's seeing what layers need to be improved and what weights need to be changed. So now that that is tested, we're also going to test in the same way our convolutional, and this will look pretty similar. This one actually has 15 evolutions, and this one's a little bit more complicated, so each epoch takes a little bit more time. So yeah, it's going to do 15 evolutions. And some of these numbers, 60,000, that's the size of the data set, so there's 60,000 images of the handwriting. And this takes a little bit. One specific thing to note is this version of the CNDK, it's a little bit easier, but it runs only on the CPU, so it doesn't use any GPU power, which is, it makes it a little bit more simpler in terms of compatibility with everything, but it also sacrifices some of the performance because the GPU can help a lot with these calculations. So you can see again, every time through every evolution, the error rate is going down, and it's already beneath. It's only on the 6th evolution, but it's already beneath our other hidden layer. network, which I believe it got to a rate of 1.64%, which is pretty good. With this, it's a little bit more complicated, the convolutional, and it's specifically designed. I think it's based on the biology of your eye and how, I'm not 100% sure on the details, but that's kind of what they were inspired by when they kind of created the convolutional learning methods.
Does everyone understand what we're doing exactly up until this point? I mean, I think it's a little confusing, especially from the first time I was going through this. Like basically though, what we've done is we've downloaded,
I wanted to know, what is the algorithm you use to like train how do you tell the neural network that this image, the face is here, and you should keep this feature?
Yeah, so once again, like I said, it's in a way very different than like a classical machine learning classification problem, such as like, taking a certain feature about it and labeling it as like cat or not cat, right? It's more about like feedback. So let's say you have you feed a picture into the neural network, right? You break it down into certain features and you put that into your input layer. And now you feed that into your input layer and say, okay, this is a cat. You're telling it it's a cat. So it'll whatever calculations it already knows, it'll do, right? And then once it gives you an output and you compare it to what you tell it is, it'll reconstruct, those little edges that we saw in the neural network? It'll reconstruct those little edges to be able to accommodate something like that in the future. So it's very feedback based rather than
so
like...
it's basically adding new features to it.
Yeah, it's not necessarily new features, but it's like the more data you're adding to train to it, the more it can almost reconstruct itself to be able to be more precise with what it's predicting.
It's kind of deciding, rather not adding more features, but deciding which features are actually the important ones that distinct the characteristics you're trying to find.
Yeah. Does that help?
I have another question. So how is this different from like hard cascades and...
Can you repeat that?
Cascades, hard cascades, like OpenCV has hard cascades which you can train to detect car or objects.
I don't know a lot about those. And you said that it's an OpenCV.
Yeah.
I think probably with R Cascade, I don't think an R Cascade uses a neural network, if anything.
Yeah,
I would think
that's what I'm asking.
I would
Like,
think
how's
it
it
uses just a
different?
classical machine, like its
Yes.
classification, right? So I'm assuming it's probably something like very traditional machine learning classification, probably like K-neighbors or something very down that road. And the difference between that, like I said earlier, is that you're taking a certain amount of training data and you're assigning features certain labels, and you're training it all at once, and just allowing it almost, just telling it directly what is related to what. So like with the cat, right, whiskers means yes, it's a cat. Or let's say, I don't know, like pointy ears, yes, it's a cat. Or if let's say it was a picture of a dog, and it was trying to, and if your problem is to classify it as a cat, if you see like flappy ears, it means no, it's not a cat. Stuff like that. Neural network, like I said, like both of us said, it doesn't train that way necessarily. So what you were probably saying with cascades is probably the latter. What I was explaining, the latter thing that I was explaining.
Okay. So now that we've actually trained our models, so these are the actual CNTK files that I was talking about. And so what we're going to do is we're actually going to make a copy of these. I'm just going to copy them. And in this copy, so this is actually what it's telling the training to do. You can see like 60,000, that's the amount of images. So this is actually the CNTK files that the library is actually reading from. And down here, these are the files that it's saying a test on. So what I'm going to do is we actually, this is in the lab. there's a resources folder, and so this is just a really small data set of images that our model hasn't seen. So as you can see, it's just pictures of numbers. And before we actually try and test it on those images, we actually have to go back and put them into a format that our model can actually read, which it gives us a nice Python script to do that. And so if you just run that. Sorry. Oh, sorry, I ran the wrong. So if we go back, it created this document, and like we saw before with the training data, this is these images. These images converted into a format that our model can actually read. So then, when we go back to our model in this folder, so this is our copy. Let's call it, or I'll open it up, or rename it to, this is going to be our custom. So down here, this is where the testing comes from. So before it was running off the test data that we downloaded earlier, but we're going to change this so that it is the data that we just created using that Python script. So I'm just going to copy the path, and then I'm changing this and save it. So then now if we go back into where our model is, we can run our custom model, and this will be a lot faster, which we run our custom model. So this will be, and so we'll see it didn't do so well. It only got 90%, or it got 90% error. So it only got one correct. But if you look, so if we look at these images, they're a lot different, and they look kind of different than the ones that it was trained on. So that's kind of some of the error, or some of the trouble, or the reason for some of the trouble that they have. So we'll do the same thing for our convolutional network, and hopefully we'll see that it does a little bit better. So we're going to have to go into here, and we're going to create a custom one of the convolutional network, and then hopefully we'll see that it does better than the one we are hitting. So let's call it custom, and I'll go in, and so we go to the testing area, and so right now it's going off that same test folder, but we want it to go to our resources one that we already created. So I'm just going to change that. Sorry. And so we're going to run our custom one. And so we'll see that it did a little bit better, but it's still not doing that well. So one thing that we can do is we can actually try it on some custom images. So we can actually go in to a cool program called Paint, and we can actually create our own images and see how they do. So I'll just create couple images. So that's a 1. And we'll put them in our other images that we tried. So this it has a little number format. So the first number is the class. It's a 1. And then the second number is just identification for multiple numbers. So the first one is 1-01, this one's 1-02. And I'll create a couple so that we can see how it is. So it's a 2. We'll save it under the same naming scheme. Let's create a few of these, just so we can see if our model can detect these custom images. And then I'll create one more. Does anyone want a specific number? I'll just create a 7. And then so we're going to have to go back and rerun that Python script for that generates the image data, because we added some new images, so we want those to be in our image data. So if we go back into this, we can see that there's now more labels corresponding with the images that we have added. So we'll go back and we can go back and see how our models do on these new images that we created. And so now we went from a 71, we went from a 90 to a 71. We have 14 images instead of 10. So our model was able to at least correctly identify some of the new images, and we'll try the convolutional network and see how that one did. Oh, that was the wrong one. Custom one. So this one did a little bit better. It went from an error rate of 80% to 64. So it was also able to correctly classify some of our new images.
And yeah, for our demo at least, I think that's it. We just wanted to show you guys what this toolkit can do. And so you guys saw what we did for this. We just downloaded some images of handwriting. Then we used these config files basically to build a neural network and classify new images and test images to see if it can recognize what digit it is. And then we even saw that you can make your own image with a certain number on it and see how that performs. So we just wanted to show you that to start off and just explain really even the power of this kind of toolkit, especially because it's open source and you guys can do basically whatever you want when it comes to deep learning with it. So yeah, and last thing is for the Amazon gift cards, we're just going to give you like a really, really simple survey. It's like your name and just like a rate, like just a 1 to 5 star rating. So if you go to that link right there, what we're going to do is once you guys fill that in, we'll give you like 2 or 3 minutes. And once you guys fill that in, we're going to randomly generate 2 numbers, and those 2 numbers will be those 2 people that will get the gift cards. The gift cards are also $50 each, so it's some spending money right there.
Yeah, and there's a lot more, if you go to the lab, there's a lot more examples and other things you can try out other than just the handwriting. They have other data sets you can try and use as well. So.
It's a capital I. After the year, it's capital.
Alright, so now we have Duke with more machine learning and no Amazon gift cards. Alright, hello everyone, my name's Duke. I'll be talking to you today about machine learning. Now, as opposed to our friends from Microsoft, I'll be talking to you more about the theory of machine learning, how it's used in research, and some interesting directions that you might want to investigate about machine learning as it pertains to your respective fields. Now, I'm a course assistant for CS 446, and I'm doing research in natural language processing and computational biology. So if you want to ask about any of those after lecture, I'd be more than happy to have a conversation with you. So the goal of this talk is to go over some definitions, go over some of the main paradigms and approaches in machine learning, some applications as it's used in computer science and elsewhere, certain use cases, so which problems you should use machine learning for, which problems you shouldn't, and what it's like to do research in this field. So definitions: artificial intelligence deals with stimulating cognition, problem solving, and learning. So what are some things that you think about when you hear the terms artificial intelligence? Okay. Okay. Yes.
Video game NPCs.
Okay. Yes. Video game NPCs are a good example. And they should act in a way that makes people think that they're actually human players, right? So yes, that's a very good example. Now, artificial intelligence is implemented in several different ways. Some of the older models, and even some of the ones used in products like video games nowadays, use something called a rule-based approach. So this is basically the programmer encoding the system with all the rules it needs to understand the situation. This can go from anywhere from programming it with the game's map and a list of ways to walk around, in the case of a video game, to programming an AI such as Siri with templates to fill in words for. And these are very simple systems, so although they're fast and easy to program, they tend not to be able to do sophisticated behavior. This leads us to our next definition, which is machine learning. This is a field that tries to iteratively optimize a policy or a classifier by using data and building models. Here we see a feed-forward neural network like the ones that we showed you earlier. And a neural network is one of the classical examples of a machine learning model. But like they showed you, you can only do so much with basic architectures. And sometimes you need to use bigger networks or train using more sophisticated algorithms. That brings us to the next thing, which is deep learning. Deep learning is a subfield inside machine learning that uses hierarchical models to learn semantic representations. One example of this is the cat classifier in their example learns to recognize ears and eyes and whiskers, even without the programmer explicitly telling them to do so. But recognizing things like facial features is difficult if you have very few layers and if you're working just from pixels. That's why we have models like this. This is called Inception. It's one of the standard architectures used in computer vision nowadays. And it's got quite a few layers. That's what, 20-some layers? And you've seen models go as far as deep as 100, 200 layers. This allows each layer to learn a different representation of the input. So for example, the first layer might learn
how to detect edges. The next one might learn how to detect shapes and fields of color. The next one might learn more complicated things, and then at some point it might learn to recognize eyes, and then from there on it might learn to recognize a part of a face, and then an actual cat at some point later on. Now, machine learning can be split up into two major areas. We have unsupervised learning on the one hand, and supervised learning on the other. Unsupervised learning learns patterns between some data points and does not need a human labeling. This has examples of word embeddings, so learning how to represent a series of words in a way that makes sense to a computer and relates to how closely words are in semantic space for a person. So for example, the words table and chair in an embedding will be closer than, say, table and student. This is a very important task in natural language processing, and one that we'll see later on. Other things are recommender systems, so recommending, for instance, shows on Netflix or products on Amazon, or clustering models, like the one shown here, or image compression. So unlike JPEG or PNG, you can get better compression ratios by learning a certain compression algorithm for that specific task. For instance, if you're recognizing just cats, all you need to compress a cat down to as small as a vector as possible is, say, maybe the cat's color, its pose, a scale of 1 to 10 how kawaii it is. Right, but you don't need to encode that much information if your data looks a lot similar already. That's something that unsupervised learning does well. On the other hand, we have things that do supervised learning. These learn to label data points and require human guidance to label things correctly. Some examples are stock market prediction. So taking in a set of data points for a stock or Bitcoin, and then coming up with a prediction for how well it's going to do in the future. This is the basis for a lot of algorithmic trading and finance done nowadays. Other things are image classification. So like MNIST, that is that they showed you before, classifying handwritten digits there. Also object detection. So in this case, we have a system that learns to recognize 2 baseball players from this image. And speaker identification. So in audio processing, if you have 2 mixed voices, how do you recognize which one belongs to whom and separate them out? That's also a supervised task. So can anyone tell me which type the naive Bayes classifier is? Is it supervised or unsupervised? Yes.
Unsupervised?
Okay, why do you think it's unsupervised?
I don't think it requires labeling of words.
Actually, the naive Bayes classifier is supervised because when you're training it, you're giving a set of features, and then you expect to produce your classifier, produce a label at the end. And so how will you assess it is by how much it labels examples as what you want it to be labeled. So that's a supervised machine learning algorithm. Next, we have 2 newer areas in machine learning that are the subject of research a lot nowadays. We have generative models. So these create structured outputs and are generally conditional upon data examples. So examples are text-to-speech systems, image super resolution, which is shown here, abstracted summarization, and automated music composition. So here we have an example of image super resolution. So it's able to take a very fuzzy image and then produce a structured and sharpened image right here. This is known as a generative task because it's generating something in a more complex domain than just producing just a number or just one word. It's something that has a lot of structure and needs to look right to a human. Next, we have reinforcement learning. This is a class of models that learns from delayed rewards. And these can be model-based or model-free. These are distinctions that influence how you train it and what kinds of things it learns. Examples are robotic control, so like your autonomous vehicles, all the robot videos you've seen. We have game playing agents like AlphaGo shown here, active learning and protein folding models in biology. Now, for instance, a control of an autonomous vehicle is considered reinforcement learning because you don't immediately get a reward. For example, a car isn't told immediately whether turning left or turning right is the correct decision in any case. It has to wait a while and then either crash or supervise successfully to get a reward. And it has to be able to assign those rewards back to which actions it took and decide whether those actions were correct or incorrect. This is actually makes reinforcement learning a very difficult task, and it's something that people are researching a lot nowadays. We've gotten very good results from it, as you can see from AlphaGo or chess bots, or like Deep Blue, way back when it was playing chess. Now we'll talk a bit more about applications that you might see from professors here or people in industry. One of them is in natural language processing, which deals with human speech and human writing. This paper is from fairly recently, and it deals with question answering. So we have a certain document, and the human requests some information about that. And it's up to the computer to provide something that's, 1, semantically correct, and 2, grammatically well-structured. So here, the question is, who did Eisenhower endorse for president in 1960? And one model says John F. Kennedy, and another model says Richard Nixon. Now one of these is correct, one of them isn't. And so these can generally be done by looking up in the document and finding words or features that it decides are important. Other tasks in natural language processing include summarization, chatbots, which generally are more sophisticated than your standard Alexa, Siri, Cortana, or whatever. These are things that after you try to understand what you're saying, beyond just template matching. Next, we have computer vision. One example of this is image style transfer. So the question for this paper is, what would it look like if a certain artist were to paint a certain scene? So we have a picture of a European village up there, and you feed the system a set of paintings from renowned artists. So we have Van Gogh here, Edvard Munch over there, and so the system generates what it would look like if Van Gogh were to paint this village. And you can see that it captures the style of Starry Night while maintaining the buildings and the sky and the river from the original photo. Computer vision is generally based on generative models because it generates either pictures like this, or the super resolution, or image segmentation, things of that nature. Next, more things in reinforcement learning. There's this paper from Google Research a while back that is very highly cited. It's teaching a bot how to play Atari games. So we have Breakout, Space Invaders, 2 other games, and a bot based on a neural network was able to play these games at better than human performance and do very well compared to human in certain cases. However, as we'll see later, these networks really aren't perfect, and so there are certain games where it fails very badly. And a lot of reinforcement learning research nowadays is based on finding out why systems break in the way that they do, and trying to prevent those in systems like robotics or swarm robotics or autonomous cars, where reliability is very important. Next, we see control. This is a picture of some researchers over, I think, Berkeley, working on teaching a robot to grasp objects and interact with them. So as you can imagine, it's using its eyes to see the scene, it's using those claws. So robotics integrates a lot of things, including computer vision and reinforcement learning, and it's considered one of the more difficult tasks nowadays. So from these, it looks like ML does everything. You've seen it do everything from process images, to text, to music, to autonomous cars. So you might be inclined to think that you just give a problem to an ML algorithm, and you'll get some sort of decent result from it. However, this is not the case. We'll see that ML has a lot of weaknesses that aren't discussed very often, and that are the basis for improved algorithms every day, and things that puzzle people in industry and research. So where does ML fail? ML loses against deficient algorithms. For example, autocorrect on your phones uses a dictionary of words and then uses the Levenstein distance between the word that you typed and a correct word and just replaces it. That's really efficient. And efforts to do the same thing with machine learning have not done as well, or have been slower, or more error prone. That's just because it's a task that we have a good solution for already, and it's difficult to learn from scratch. Next, we have bad worst case performance. So like an autonomous vehicle crashing, that's been in the news quite a few times. Or this case by Azegedi in 2013, this is the canonical example of how machine learning algorithms can fail. We have a picture of a panda that it classifies fairly confidently. We give it a tiny bit of noise, 0.7% of noise, and it now thinks this is a picture of a monkey. So obviously these models aren't learning what it means to be a panda, or what it means to be a monkey. It's learning something about these images, but we're not really sure what. Next, this ties into poor replicability. So a system that you train and does well on a certain task might not do as well when you train it again and give it the same task. And that's very much an issue when the security of a system is at stake. And finally, we have unintuitive failures. So like this again, why does adding a tiny bit of noise make it think that a panda is a given? Who knows? And when systems like this fail, it's very difficult to find out why it fails and how to fix it, as opposed to an algorithm that you design deterministically. On the flip side, there are certain tasks that ML does very well. These are well-defined problems with nice algorithms. So, for example, robotics. It's very difficult to tell a robot how to grasp an object without hard-coding all the possible scenarios. And that's why teaching it to learn how to grasp those objects and to manipulate things in its world, that's why ML works well for that. Same thing with computer vision. It's very hard to tell the computer what it means to be a cat, and by having the computer learn on its own what those objects are, that's something that ML is very good for. Also, problems with large data sets. You saw MNIST, for which there's tens of thousands of handwriting examples. So that's enough for it to learn from the ground up how to classify data. Also, problems not well solved by humans, or problems with underlying structure. There's something in literature called Manifold Learning, and that's when it learns to extract things like this curve in latent space. And in those areas, it might not be immediately obvious to a human that there is a pattern if you're just looking at the marginals along each axis. But the functions that a neural network learns or SVM learns can be very good for extracting this hidden structure. So even after you've learned what ML does well and what ML does poorly, you might be inclined to take this up as an area of research, because let's face it, it pays well. The work is interesting, it's flashy. But on a day-to-day basis, researchers develop and train models. They work closely with domain experts like linguists and biologists. They keep up to date with literature in mathematics, statistics, computer science, and they work in all these fields. So you might imagine, for example, someone working in autonomous vehicles would work very closely with people in electrical engineering to develop better cameras, work closely with mechanical engineers to ensure that the cars are as well tuned to receiving inputs from a computer as possible, and people in business to make sure that marketing expectations they're setting are realistic for the safety that they're getting with these cars. Now, to get involved in machine learning, the most important thing is a solid understanding of mathematics. All of this is based on linear algebra, statistics, functional analysis, and it's important to have a good grasp of these, and that's why those are prereqs for machine learning classes, incidentally. Next, a willingness to read and understand papers. Research gets published at an astonishing rate in this field. So if you look on arXiv, machine learning is probably one of the biggest categories on there, and there's at least 5 to 10 new papers every day. Creative problem-solving skills. So models like Inception, which you saw earlier, don't just come up as a routine consequence of iterating upon old ideas. There's a lot of creative freedom when it comes to deciding what sort of architecture is appropriate for a certain problem, and that's something that requires problem-solving and it requires a certain level of intuition. Next, you need full software stack awareness. So this is everything from understanding what tasks the GPU versus CPU does well, to problems of handling the noise that you see in your inputs, to seeing when it's appropriate to switch between different frameworks. And lastly, you need a good deal of patience, because sometimes your models will fail and you just won't know what's going wrong, whether it's something with the hyperparameters, whether the data's noisy, whether you just need to scrap your model altogether, or whether it just hasn't trained enough. And even in the best case of everything going as planned, training a model might take a few days to a week if you see any real results. So this is just some examples. This is a typical paper you might see. This is the Mori lemma. It's an example of how to take a continuous space, represent only a few points in there, and get something that approximates the structure of the whole space. There's a lot of math, right? And on the right here, we see a model that's failing. This is the same thing as style transfer, back with those paintings, except it doesn't look to be as successful as that previous one. We see it changing a dog into what it thinks is a cat, but is obviously still some sort of dog. Or turning a cat into a dog and incidentally raising something hideous, right? Or turning an apple into an orange that's just obviously recolored. Or turning a zebra into a horse, but it's obviously still a zebra. And when you see these, it's very easy to blame the system and to just give up, because honestly, it's very difficult to tell what's causing these errors to happen. But let's say you accept the fact that you'll be spending most of your days reading and debugging things that don't work for whatever reason. So how does one get started in machine learning? First of all, there's a very nice toolkit in Python called Scikit-learn. This has pre-trained models. So you can just import an SVM, import a neural network, and just say, train it on this set of data, and then run it. That's a lot like what our friends over at Microsoft were showing you earlier with their CNTK. But Scikit-learn is open source, and it's built for Python and meant to integrate well with other Python products. We can go over a short demo of this if we have time later. Next, this is an online course that's very popular among the machine learning community. So this is just like if you ask anyone how to get started in machine learning, they're going to point you over to this course. It's on Coursera, supported by Stanford, and it's taught by one of the leading minds in the field. Next, once you've done Scikit-learn, you understand a bit more about what a model is supposed to do. PyTorch is something that's developed by Facebook AI Research, and it's generally considered to be the fastest toolkit out there. So this has GPU accelerations, so you can use the GPU in your computer without needing to work in CUDA or in something like Piano. That's a lower level. It's really nice, and most work that's being done in academic research is being done in PyTorch. And then finally, more resources. Our professors here are excellent. We have a machine learning class, that's CS498. This is an applied class, so you'll be learning more about how to implement these models and less about the scary math that goes on behind them. We also have an ECE course, Introduction to Big Data. That's very applications focused on, say, signal processing, image processing. So that's more from like an ECE perspective. You're going to get like a different outlook on it. We offer CS446, which is a more mathematical and proof-based machine learning course. CS447, which is natural language processing, and CS445, which is computational photography. Course offerings change every semester, and these are just like some of the ones that have been around for a while and have known to be very well taught. Now, in terms of independent reading, here are a few good textbooks. Deep Learning by Goodfellow, Corville, and Bengia. This is the standard deep learning textbook. It talks a lot about neural networks, why convolutional neural networks work well with photos, why recurrent neural networks work well with text, different ways of training them, besides your standard gradient descent. And it goes a lot into like more esoteric machine learning as well. Artificial Intelligence: A Modern Approach by Russell Dorfing. This is the textbook we use for our CS440 Artificial Intelligence class. And lastly, Introduction to Statistical Machine Learning by Sugiyama, which takes a more statistics and mathematical-based approach as opposed to it stimulates the brain, right? Because that's not entirely helpful. Now, given that there was some ambiguity about backpropagation in the previous lecture, I'd just like to explain how backprop works. So this is a neural network with one hidden layer. We have an input, a hidden, and an output. So these are initialized with generally random weights at first, so there's going to be absolutely no understanding what's going on. So you pass in your input, it gets multiplied by some matrix, squashed down, whatever. You get your hidden layer, you pass it through another matrix, add another squashing function, and then you get your output. And so, let's say you pass in your digit of a 1, it classifies it as a 2. There is a certain error there, and based on that error, you can calculate the gradient of that with respect to this middle layer, and then do gradient descent. So go down the slope of your gradient towards something that's more optimal. So it's kind of like asking, what changes to these weights could I have made to make it more closely give me the behavior that I wanted? And so you incrementally change these connection weights, which are, I guess, like the synapses in the brain. And so ideally that takes you closer and closer to a correct classification. Does anyone have any questions about this part? I know there's some ambiguity about it earlier. Yes?
So you mentioned gradient descent. Is it an issue to find like local optimizations and not like absolute?
Sure, yeah. So local optima are a big problem, and a lot of research has gone into determining how many local optima there are for a certain neural network, and how easy it is to get out of them. The general consensus is that there are local optima, and there are a lot of them, because the surface that a neural network learns is very complicated. There's a lot of local optima, but just the fact that we're doing gradient descent sometimes causes it to jump out of this local optima. And so there are two hypotheses. The first one is that it's mostly convex, so it'll go towards the global optima in the vast majority of cases. Or the second hypothesis is that there are a lot of local optima, but all of these are close enough to the global one that it doesn't matter which one you end up in. Good question. Any other questions? Okay, seeing as no more questions, thank you for your time.
Go. Unless you have questions about